Fine, sir. Audio visible.
Yeah.
Video also visible.
Okay, thank you, sir. So we'll wait for a couple of more minutes and then we'll start. All right, I think we can start now. It's almost time. So yeah, good evening, everyone. Welcome to the first out session of the course Finite Element Method, Variational Methods to Computer Programming, which is a part of the NPTEL initiative. And first of all, I would like to introduce myself. My name is Omer Hussain, and I am a PhD scholar in the Department of Mechanical Engineering at IIT Madras, and I am a PMRF fellow. So, and my research area is related to computational material modeling, and I'm specifically working on the modeling, the computational modeling of the chemomechanical coupling in the lithium-ion batteries. So, since it's a very first session, so I would like to know about you all. I would like to have a brief introduction of you all. What are your backgrounds and what is your motivation for the course and uh, what are your aims and what do you expect from the course basically? So would anyone volunteer to introduce themselves?
Hello, sir.
Yes, sir. Yes, sir.
Uh, Good evening. My name is Unni Karta. I am a faculty member at Federal Institute of Science and Technology in Kerala. I am basically from the Department of Civil Engineering. So I have been teaching for quite some years, almost 20 years now. Right now, I am teaching for the PG program in structural engineering, where I am engaging the classes for finite element method. So even though I've studied the subject and taught it, I thought I will refresh and understand, have a better, deeper understanding of the subject through this course.
Okay,
So
sir.
that is why I'm attending. Thank you for the opportunity.
Thank you, sir. And I think with your experience, it would be a learning opportunity for me as well. Uh, okay, so is there anyone else who would like to introduce themselves?
Yeah, hi, Umar.
Hello, sir.
Good evening. Yeah, I am Sandeep Singh. Basically, I am working MNC, and my work involved in this CFD analysis, finite element analysis. So, just I wanted to refresh my fundamental knowledge, so that's why I registered in course. Yeah,
Okay, sir.
yeah.
So,
Thank
do
you.
you have any background in FEM? Have you taken any course or
Yeah, yeah.
exposure to?
During my engineering, I have basic understanding and this
Okay,
FE.
okay, nice.
Thank you.
Okay, thank you, sir. So, yeah, is there anyone else?
Hello, sir.
Hello, yes, sir.
I am from BTech Mechanical Engineering
Okay,
School. One.
okay, sir.
Yes.
Okay, thank you, sir. Yeah. So, yeah, anyone else?
Sir, good evening. This is Juhi Kushwaha.
Yes. Good evening.
So, I just got registered for the course as a part of my PhD program, which is going on right now.
Okay. So, from where?
So, that's the reason why I've taken the course.
Okay, from which institute?
I am working in Hyderabad.
Okay, ma'am.
My PhD is going on from IIT Mandi, Himachal Pradesh.
Okay, nice. Nice. So you've had any background in FEM? Have you taken any course or worked with FEM before?
I do 1D FEM for thermal analysis. I have not done any professional course as such, but I have taken the background knowledge from books. So I thought this PhD program is a good opportunity to do a course. Yeah.
Okay, ma'am. Thank you. Nice. All right. So I think we have new participants too. So if anyone would like to introduce themselves from new participants, introduce yourself and tell your motivation and expectation from the course. All right. I
Hello,
think yes, yes. Please, sir, go ahead.
I'm Suraj MG. I am currently working in EDA Aeronautical Development Agency as a contract engineer and just want to take up this course. I finished one course from composites, which was given by IIT Guwahati. Now I am taking up this course on this FEA course. I just wanted to see, how it is. I was interested in calculus, so I just took up this course.
Okay, okay, sir. Thank you. All right, then if we don't have anyone else, then shall we move forward?
Yes, sir.
Okay, thank you. So, we have weekly doubt sessions for this course, as you all might know. So, in the way I am planning to keep this doubt session is to first take some time in discussing the quick summary of that particular week's content. We'll quickly go through all the content that we had covered in the video lectures, and then we'll have a doubt session. I will discuss some questions that I prepared on my own and some previous year questions also. So then we will discuss, and meanwhile, through the entire discussion, at any time you all are welcome to unmute yourself and ask any doubts. So we'll discuss, and of course, we have people from various background, industries also, and academics also. So I think it's going to be a fruitful session for you as well as for me also. All right, then we'll start with the week 1 content. So first of all, about this course, this is course name is, as you can see, it's a finite element method, variational methods to computer programming. So in normally when we talk about FEM, we don't always see the term variational methods or variational principles. And I don't know if anyone has done any other NPTEL course on FEM. Actually, last year I had been TA for Basics of FEA Part 1 course. So that is also a very nice course for building fundamentals. But this course starts in a different way, variational methods. So variational methods basically gives you a way to arrive at the governing equation of the problem. So in FEM, we generally start with a strong form, and as we'll go along, we'll see that we can get a weak form. If you had taken FEM before, you know, strong form and weak form, and that's basically our starting point. And then we do all discretization, everything, approximation. But in this course, we take a step back and see how variational methods can also help us arrive at a governing equation or the main problem. So, but by the way, the variational method it in itself is a a course in itself. So it's a vast course, and I don't think we in this for this particular course, I don't think we'll be going to go much deep into it. But it has more detail to it than you'll see in this course. So. In fact, a lot of normal problems that we solve using Newtonian mechanics, like simple spring mass system, all that can be done using variational methods. So that in that case, that is called Lagrangian mechanics. So we'll not go much detail about it, but we'll start with what is relevant to us in this course. So in variational calculus, we mainly focus on to the minimization problem. So what are we going to minimize? So we minimize what is known as a functional. So would anyone like to define functional? Any definition that you know that's not written here, like something new? Would anyone like to answer this? What's a functional?
Function of a function.
Yeah, that's a very fundamental. It's a nice definition actually. I would like to write it here. Function of a function. All right. So yeah, basically functional is a function of a function. It's a very crude definition, but it's a nice definition. So we have various functions combined together into a form of a bigger function, and that is integrated over some domain. So and in mathematically, what it is defined as a mapping from a function, say some function y(x) to a scalar constant. So here, this term I here, this is a functional, and it is defined as an integral of some complicated function of a function y and its derivatives. The derivative can be first order, second order, any order derivative. So that's basic functional in 1D. So we have, so here x is uh, independent variable and y is the dependent variable, and further are the derivatives of y with respect to x, of course. Okay, so as I mentioned earlier, so what the complete course of variational calculus revolves around minimization of this functional, and this minimization of this functional gives us the function. So we need to be, the basic problems in variational calculus look like we need to find yx such that this I is minimized or extremized, basically can maximize also, but we generally talk about minimization. So a typical example of a variational problem is the brachiostrone problem. So in a brachiostrone problem, we we have 2 points, point 1 and 2, and we need to find a path between point 1 and 2 such that a particle falling freely under gravity takes minimum time to reach point 2 from point 1. So uh, so as you can see that we have to minimize time. So if we can write the time of this total travel of the particle from point 1 to point 2 in form of a functional, then basically that becomes a minimization problem. So here you might have seen in the video lecture that we can define the time here in terms of uh, the the y and its derivative. So minimization of this functional t will give us our path yx, path of travel. Yeah, so find yx such that functional t is minimized. So but how do we minimize it or extremize it? So consider any functional I, which is a function of that independent variable x and dependent variable y and its derivative. So we'll consider only first derivative. So let us assume that uh, the extremum value of I is achieved for particular a particular value of y, that is yx. And let us assume that at the end points x1 and x2, the value of y is known. So we consider so any other value of y. Uh, uh, so if we substitute y with any other value, say y dash y tilde, which is this is the minimum value, and if we add any other function to it, it will not be a minima or an extremum. It will be divided from the extremum value of I. Some it will give some I which is not a minimum. And if so it is y tilde is defined as y plus epsilon eta, and if this term epsilon eta becomes 0, then we get a minimum value. So we can say that I tilde at epsilon equals to 0 becomes I. So basically at epsilon equals to 0, it gives the extremum value. Let's say extremum. So if we write the Taylor series expansion of I tilde about epsilon equals to 0, we'll get an expansion like this. And from the fundamentals of maxima and minima, we know that the necessary condition of epsilon equals to 0 to be an extremum, the first derivative, or the which is it is known as first variation, should be equal to 0. This is the necessary condition. Further, there are more conditions to determine that if it is maxima or minima, but we won't go into much detail about it. So we need to find the so this equation first variation equals to 0 basically will give the extremum, uh, the y corresponding to the extreme value of I. So now you might have seen the derivative, the derivation. I won't go into much detail about it. So at the end, we get to an equation, something like this. So this equation is known as Euler-Lagrange equation. So the problem defined in the way that find y such that the functional I is minimized or extremized. Uh, that y can be calculated from the differential equation arising using the Euler-Lagrange equation. So if the problem posed in that way and the problem posed by Euler-Lagrange equation mean the same, so both of these definitions represent the same problem. So if we solve this Euler-Lagrange equation, we solve y for in this Euler-Lagrange equation, we get the y which extremizes or minimizes the functional I. So at the end, we see that the variational mechanics converts a minimization problem to a strong form, or in sense of mechanics, we call that equation of motion. Okay, so now if we have multiple dependent variables y1, y2, and corresponding derivative, so again the minimization of the functional I for the extreme will give us the corresponding Euler-Lagrange equation for each of the variables. So we'll get a coupled system of equation for that case. So it's kind of straightforward. And similarly for we also saw that for higher derivative terms in the functional, we'll get a more complicated Euler-Lagrange equation where the each subsequent terms added corresponding to the higher order derivative it has a pattern. We add a minus sign and plus sign alternatively, and the order of derivative increase. So we also not go into much detail about it. So in FEM, we'll see something known as strong form and weak form. And so basically, whatever the governing equation is given to us. In FEM, we can convert into an integral statement, which is also known as weighted residual statement or variational statement. This can be written as so we'll discuss this later in detail when we start FEM. So basically, essentially, this also these two things also mean the same. Okay, so so the in FEM we essentially convert the strong form into a weak form or which is known as a weak in an integer statement. Can anyone tell why is the weak form called weak form, or why do we care to go into weak form for FEM?
Sir,
Yes.
in weak form, the solution may not satisfy at every point in that. I mean, the solution function will not satisfy the governing equation at every point.
In weak
I
form.
mean, the weak form.
But my question is, why do we choose weak form? Why do we go into weak form?
Uh, because we can use an approximate solution.
Yes, but we can also
Yeah.
approximate solution in the strong form also, right? We can do an approximation
Okay.
like we do in I think Rayleigh's method. I think we do that.
Yes.
So
Uh,
what advantage does weak form has over strong form?
I'm not very sure about that.
Okay, fine. Would anyone else like to try? Okay, so weak form, as the name suggests, it weakens something. So what it weakens is the differentiability requirement of the approximation solution. So if you see that if I want to approximate a solution u here, it should I can't assume say a linear function ax plus b. If I substitute there, it will turn to 0, and I won't get any solution. But here, if I here this won't work. But if here I substitute a solution ax plus b, so here only u is differentiated only once, and it will not blow up. It will not go to 0. So the aim of the weak form is that the differentiability requirement is reduced, and we can use lower order polynomials for the approximation, and that causes a lot of reduces a lot of pain in solving those polynomials and evaluating them. Okay, so in weak form we have something known as bilinear operator and linear operator. So we'll see look into that later in detail. But just quick definition of linear. Can someone define how do we test the linearity? What is the test for linearity? Two conditions are there. Can someone tell me? When is an operator called a linear operator?
Superposition.
Yes. That's I think that sums up everything. Superposition. So if we'll talk in simple language, we if we are defining an operator, so we're defining some operator t on some function u. So the condition for linearity is that if we break replace u with u1 plus u2, it should give t of u1 plus t of u2. And second condition is, oh, sorry, if we multiply a scalar constant with this function u, it can be taken out of the linear operator. So if these two conditions are satisfied, the operator is known as linear operator. And what is a bilinear operator? So bilinear means linear in two ways. Bi means two. So first of all, the operator should be on two functions. So if it is linear for both, like we can see in these two conditions, it appears linear for both. Then the operator is known as bilinear operator. So we'll see that we at certain situations we need to see that this term, which is some operator of w and u, w is the weight function, u is the primary solution. This would be tested if it is bilinear or not, and symmetric also. Symmetry is kind of straightforward. We interchange u v with vu, so we'll see why. So initially we started with a minimization problem, and we saw how we can go to a strong form or the basic differential equation form of a problem, and then we briefly discussed that the strong form is also equivalent to a weak form, where that is an integral statement of the problem. So these three things represent the exact same problem. There's no approximation, nothing. Exact same problem. So the ways to arrive from one to another is, from for minimization problem to a strong form, we need an Euler-Lagrange equation. If we solve, if we Euler-Lagrange equation converts the problem, and then if from strong form to weak form, we need to write the weighted residual statement. We need to multiply the equation with a weight function and integrate and differentiate it by parts. And again, from weak form to go to a minimization problem, first of all we need to satisfy the condition that the two operators, if we this is a weak form here, if this is one operator, this is another operator, L, function of w, so this should be bilinear and symmetric, and this should be linear. If these two conditions are satisfied, then we can convert the weak form into the minimization problem in this way. The functional would be defined in this fashion: half of the bilinear operator on v comma v. V is the weight function or the test function, minus the linear operator on v. So we'll try to see by considering simple examples how this can be achieved. So now next part that we covered is the approximate solution to solve the differential equations in 1D. So first we have the weighted residual method. In weighted residual method, first of all, can someone tell me what's a residual?
The error in the
Error?
solution
Yes, error for what?
for the approximate solution we have assumed.
Yes, exactly. So if we have the differential equation of this form here, we can first we can write this as d by dx of a du by dx plus f of x equals to 0. So whatever the solution for u is, if we substitute it here, we should get a perfect zero. That's the exact solution. But if we are approximating u is with some approximation, say un, so if we substitute this approximation here, we'll never get a perfect zero. They will always have some error here. And this error is known as residual. So when we approximate a solution, we can't have a zero error at all points in the domain. But what we can try to do is we can minimize the sum of error at each point. So if we so in order to do that, we solve the weighted residual statement. We write the weighted residual statement. So if this residual multiplied by some weight function and is integrated of the domain, so the sum of this error, weighted error, should be equal to zero. That is what we that is how we try to minimize the error in our approximation. So based on the choice of weight, our weighted residual method is further classified into Galerkin method, least square method, and collaboration method. So I think for this course we don't need to go into much depth about it. If there's any doubt, you can please ask. We can discuss further. So in the last approximation method is the Rayleigh-Ritz method. So in Rayleigh-Ritz method, again we start with a weighted residual statement, but we convert into a variational statement. That is, we in simple FEM terms, we convert it into a weak form. So suppose earlier we had that equation. So if we multiply it with some weight, so this is our weighted residual statement. If we integrate it by parts, by the way, if anyone has a doubt in how are we doing the integration by parts, you can please ask. So so in Rayleigh's method again, so we uh, convert our weighted residual statement to weak form, and then we approximate the value of u. And u is approximated in terms of some functions in the following form: cj times pj. These can be as many number of approximation function as accurate solution we want, plus a function phi naught. So the thing about this function phi naught is, okay, let me ask you, can anyone tell me what should how do we select the two functions phi naught and say phi j? Suppose if I want, if I approximate it as at c1 c2 plus p2 plus phi naught. So what conditions should these p1 p2 phi naught satisfy for our for this for substituting here? Can anyone guess?
Should be polynomial.
Yeah, yeah, of course we'll go for polynomial, but that is not necessary. We
Uh,
generally go for polynomial to make things easy for us, but
yes.
that is not always necessary. We'll discuss a problem in which I'll show you that we are not taking polynomial.
Should be differentiable.
Yeah,
Continuous.
of course. These are, yeah, correct conditions. But apart
Yes.
from these two, is there anything else? Okay,
Mm,
would anyone else add into it? These two are correct. Okay, so I think I'll tell. So for phi naught, we should ensure that it satisfies the boundary conditions. And if I think if I'm right that it should only satisfy the Dirichlet boundary condition. I think satisfying Neumann boundary condition is not necessary because this Neumann boundary condition would come in this term here it's directly. Uh, and for phi 1 and phi 2 they should satisfy the homogeneous form of boundary conditions. Same boundary condition, but they're homogeneous forms. What does homogeneous form mean? Anyone? Homogeneous boundary conditions. Anyone heard of it? So in this problem, we are given the boundary condition as u at x equals to 0 equals to u naught. What should be the homogeneous form of this boundary condition? Anyone, any guesses? All right. I'll tell. So homogeneous form of this boundary condition means that it should be 0. Homogeneous means the right hand side is equal to 0 in general sense. So so why do we need homogeneous boundary condition for phi 1 and phi 2 and not for phi naught? So this is because if we have assumed un as c1 p1x plus p2 p2x plus p naught x, and we want to evaluate un at x equals to 0. So this at x equals to 0 system would go to 0, at x equals 0 this term would go to 0, and this term will give us u naught. So it will easily satisfy the boundary condition. It won't have to any of the contribution from c1 c2 those terms would not interfere with the boundary condition. So that's why it is safe. These phi1 and phi2 are assumed safely by satisfying the homogeneous form of boundary conditions. Okay, so this week we finished that the related method. Uh, so that's all to discuss regarding week 1 content. Is if there's any doubt regarding whatever I have discussed so far or whatever was in the video lectures, you are please welcome to ask now. We'll wait for some time if anyone wants to ask any doubt. We'll try to discuss and solve the query.
So this is not a doubt, but we'd like to know which textbooks has the same treatment which you're giving for this lectures course.
Uh, I'm sorry.
Is
Textbook
there
of
any specific textbook no, which will give the same treatment? Because I have referred to a few finite element textbooks, but the treatment given in your course is different
uh,
from many of those.
yeah.
So I was wondering which textbook will be good.
For this particular course, this is the way it has been structured is also new for me. I have taken courses in FEM and I have taken a separate course in variational methods, but I have never
Okay.
come across any course which combine these two. But
Okay.
I guess that this book by J.N. Reddy,
Okay.
there's
Okay.
a normal FEM book by J.N. Reddy where you will get all this fundamentals of FEM, strong form, weak form, Taylor-Ritz method, weighted residual, everything. But
Yes.
I remember this another book by J.N. Reddy which talks about the variational methods. I'll look for that book and let you know in the next session maybe.
Thank you so much.
And there might be another some more books on variational principles. I'll check if I can find any. I That's a long time back I did that course, so I'll have to look out. I'll let you know.
Yeah, thank you.
Yes. So apart from doubts, is there any suggestion, feedback, or anything you want to discuss here? You're free to unmute yourself.
I just have one question to ask.
Yes, ma'am.
In week one, yeah, in week one, lecture three,
Yes.
which is discussing the Rayleigh-Ritz method, one numerical has been solved. Sorry, not the numerical. It is shown that a functional is bilinear and symmetric.
Mhm.
So there it has been solved for argument one, and then it has been given to prove the same thing with argument two. So I did not really understand that how do we prove the same thing with argument two?
Okay. So I can't recall what exactly were the argument one and two. Is it about checking for
Argument it
bilinearity of?
is
Yes, please go ahead.
it was minimization of a functional using the variation variable, wherein y was replaced as uh, alpha u plus beta w.
Okay.
This was argument one.
Okay. Why
Do
was
you?
yeah? I'll
I mean,
try
can
to
you
write.
refer?
Yeah. Can you speak that? I'll try to write that what you're trying. So
Just
there's functional I. Is it a
okay,
functional
can you
or an
just
object?
give?
Yeah, please.
Yeah, can you just give me some? It's a functional. If you give me 2 minutes, I'm trying to open the lecture.
Yes, sure,
I'll just tell you exactly what we had to do in that.
sure.
Do you have access to the week one lecture three?
I have. I'll just check. Just give me a minute. Week 1, lecture 3.
Okay.
Okay, can you tell me the time stamp?
We have
Just a second,
minimum.
I'll tell you. Is there any possibility of writing it through an email or something?
Yeah, I think there is uh, some Google group for the discussion. There's some discussion forum. I am not sure where you can find it. Uh,
Okay.
Somewhere in the lecture.
There is a
There's
discussion forum, sir.
yes. Ask a question. There would be a link at the top. There will be a link for ask a question. That will take you to the Google discussion forum. So there, I think you can post it.
Okay.
I'll try to see there if I can answer that. I'll try. Okay.
Okay. Thank you.
No problem. Yes. Anyone else have any doubt? Okay. So I think if there's no doubt, we can move forward to the next part. So we'll have a discussion on some problems. So I will hope to have an active participation in this. So yeah, consider a problem. There's some governing equation for finding the fundamental frequency of a circular membrane. Uh, don't have to worry much about what the problem is about, but so this is this is our strong form or the governing equation of the problem. And so consider a variation statement for the above problem. So this is some random variation statement that is related to the above differential equation or strong form. So we need to find the value of n, l, and m here. So that this variation statement represents the above problem, and we need to find psi r and okay, we'll discuss it later. First of all, how do we arrive from strong form to the variation statement? Anyone would like to start? Guide me here. So, what is a variational statement? By the way, I quickly went ahead into this variational statement, but I didn't discuss much in detail. I hope whatever was covered in the lecture was clear for you. I hope there's no doubt about what is variational statement, what is weak form. Yes, so would anyone like to tell how do we start? We integrate over the domain. Strong form, or we'll make it easy, rather easy. We'll multiply the equation by r first. And we multiply it with some weight function. Weight function, or this is also known as variation of u. This v is known as the variation in u. Okay, so this is how we start for writing the variation statement. And what do we do next? Anyone?
Part integration.
Yes, yeah. Integration by parts. So we have double derivative on the first sum here. So we'll do integration by parts for this term. We'll have plus. So how do we proceed? We for the integral term we transfer this derivative, outer derivative here on the variation variable. We get dv by dr, and the rest would be like this du by dr times dr. And then we have boundary term, so we'll be left with b r du by dr. And the other term can be written as it is. And vu dr. Now if we'll try to break this boundary term, I'll write it here. So we have b r at a du by dr at a v. I'm sorry, not r at a. Actually, v at a, v at a, and r itself is a. V at 0 and r is 0. Du by dr at 0. So we have what is the? I think I forgot to write the boundary conditions for the problem. Okay, let's check and write it. Just give me a minute. Yeah, so boundary condition for this problem is u at r equals to a equals to 0, and other one is du by dr at r equals to 0 equals 0. So at r equals to a, we know u. So if the value of function is known, its variation becomes 0 at that point. And here of course we already have a 0 term, and du by dr is also equals to 0. This term goes to, both term goes to 0, and we are left with 0 a lambda r u dr. So this is the final variational statement that we get. dv by dr or du by dr to dr equals to integration lambda r vu dr. So this is correct. So what is the value for n? N here is the power of r. What is the power of r? Here is 1. So n equals to 1. What is the value of L? L here is the power of dv by dr, and the power of dv by dr is 1. And m here is power of du by dr, and the power of du by dr we get is 1. So all three, n, l, m are 1. Fine. And to find psi r, psi r is the, it's like the integral on the right hand side, which is the coefficient of vu dr. And here the coefficient of vu dr is this. So psi r is lambda r. So by simple comparing the variation statement that we got with the given, we get all these values. Fine. Is this clear? How we got to the variation statement? Next, so next question is interesting. So what condition should L and M satisfy for a minimization problem? So if you can recall how we can go from a variational statement to a minimization problem. What are the conditions there? So to give you a hint, this term can be written as an operator A on nice.
Is equal to
Yes, sir.
L is equal to m condition to satisfy the condition.
Sorry, you are not audible.
L is equal to m
Yeah, L equals to M.
condition of satisfied equation.
Yeah, but why? I'm asking. Yeah, your answer is right. It's absolutely right. But what condition should the variational statement satisfy in order to get a minimization problem? Okay, so the answer given is correct. L should be equals to M. But why? So if you see that the variation statement that we got here, r to the power n, so can someone tell me which term is the bilinear term and which is the linear term here? Anyone? the bilinear and linear term. Anyone? Bilinear, linear. So first of all, what is the primary variable here? U. And what is the variation in U? That is V. Or this is known as weight function, test function, different names. So both of these terms can be written in terms of simple operator on V and U. Okay, so in order uh, to get a minimization problem from a variation statement, the equation should be written in the form of equals to LV, and this term should be bilinear term, and this term should be linear term. And turns out that we we have this term as LB equals to 0. So we don't have this term here. So it is automatically linear for now. But we have these two terms as the operator AVU. So first of all, the second term is clearly bilinear. It bilinear and symmetric. Sorry, it should be symmetric also. So it is clearly symmetric. We can interchange V with U. We'll get the same function, and it is since both V and U have the power 1. So if we replace V with V1, V2, and or replace U with U1, U2, we can simply break the operator into two operators on V1 and V2 or U1 and U2. So this is simply bilinear. But this first term has to satisfy the condition that L should be equals to M, whatever the value of L and M may be. If it's 2, 3, 4, but these two should be equal in order to make it okay. In order to make it symmetric, these two should be equal. But to make it bilinear, should be equal to 1. Both these should be equal to 1. So if we take L and M equals to 2, so we'll have power of 2. We can't break d of v1 plus v2 by dr whole square. We can't get the operator as a of v1 plus a of v2. This won't be possible if we have a square term here. So these L and M should be equal to 1. The correct answer is this. L should be equal to M and these two should be equal to 1. Correct. So the main condition that we need to check is that we should have the operator A should satisfy bilinear and symmetry, and the operator L should be linear. Okay. Is there any doubt here? If not, then shall we move on to the next problem? Okay, so we need to basically find the minimization statement. Sorry. So how do we write the minimization statement? First of all, we need our the operators to be bilinear, symmetric, and linear. And if they satisfy this, we can write it as half of AV comma V minus LV. Remember this statement? So LV is 0 for us. and what is AV comma V? So AV comma would be whatever we have written here. We'll just need to replace U with V. So we have R to the power. So we got R to the power 1, and dV by dr also equal to the power 1, and du by dr also equal to the power 1 times dr. Then we had lambda r u and v, so we get v square dr. So this is our functional minimization function for the problem. Now can someone tell me what should the value of m, b and c? I'm sorry, this should be v. So we can compare the function that we got with the given in equation 3. We get m is the power of r, which is equals to 1. B is the power of dv by dr, which is equals to 2. And c is the power of v in the second term, which is equals to 2. So this should be the answer here. So is it clear for everyone? How do we get the minimization statement? Okay, if there's no doubt, can we move on to the next step, next problem? Okay, so for the above problem, if we try to solve it using the Rayleigh-Ritz method, by assuming the following form of the approximation, U equals C1 Phi1 plus Phi naught, where Phi1 is cos QR, then what should be the choice for Phi naught, and what is the general form of Q? So please, I would need answers from you. We discussed this minutes before at the end of the first session. So how do we choose Phi naught? What are the conditions for choosing Phi naught? Anyone? Anyone would like to guess? What is simplest choice for Phi naught?
Should satisfy the Dirichlet boundary condition.
Exactly. So the Dirichlet boundary condition here is it should be 0 at r equals to a. Exactly. So what is the simplest function that can give this? So simplest thing can be we take it as 0. So it's 0 everywhere. We don't have to worry about it. It automatically satisfies the boundary condition. Or we can take any function. which is like r minus a. It will also work. Okay, so yeah, that can be the choice for phi naught. And so what is the general form of q? That basically means what should be the choice of phi, like how should we choose phi1, and for that we need to choose q. So what would be the answer for part B? So what so what condition should it satisfy cos qr for it to be our choice for phi1 in Rayleigh-Ritz method? Anyone? Anyone? Any guesses?
Should should satisfy the homogeneous condition
Yeah,
of boundary condition.
yeah. Homogeneous form of the Dirichlet boundary condition that is given. So, in fact, for us in this problem, the given Dirichlet boundary condition is a homogeneous boundary condition. So, it's the same. So, basically, it should be that phi1 at r equals to a should be equals to 0. So, that means cos of qa should be equals to 0. And when does cos qa give 0? When does cos give 0?
Pi by 2.
Yeah, pi by 2 or 3 pi by 2 or 5 pi by 2. So if we replace this with, I think, 2n plus 1 pi by 2a. Hopefully, I think I'm right. Please verify this. We'll get 0. So q should be 2n plus 1 pi by 2a. Fine. Is it okay?
Can you please explain it again? The B part.
Yes, so we're asking that what should be the general form of Q in this approximation cos QR. So what condition should phi1 or cos QR satisfy in our approximation? That it should satisfy the Dirichlet boundary condition or the homogeneous form of the Dirichlet boundary condition. So the Dirichlet boundary condition is already homogeneous, so which is at r equals 0, it should give 0. So phi1 also should give 0 at r equals to a. So that is only possible if our so cos so our phi1 is cos function and cos is 0 at pi by 2, 3 pi by 2, 5 pi by 2, or in general sense 2n plus 1 pi by 2. So at r equals to a, if we so if where q is of the following form, this form, then at r equals to a, this the argument of cos will become 2n plus 1 pi by 2, and it will always give 0. Is it fine?
Okay.
All right. So can we try to solve this problem using variables. See, so we had two integrals here. We'll try to solve it using the Taylor-Ritz method if we can. We'll just quickly see how to do it. R dp by dr to du by dr lambda r. So we are approximating u as c1 c1 phi1, right? And phi naught is 0. So this becomes c1 cos qa, sorry, qr. And we since we have only approximated u with just one function, we can take v as phi1, that is cos qr. So our integral statement would become 0 to a r times, sorry, it's derivative of v and u, d by dr of cos qr, and same thing, the square, 0 to a lambda r. No, it's not the same thing. We'll have a c1 also here, and similar c1 here also, cos qr square dr. So turns out that in relay-rates method, what we do is we write this integration statement. We get an equation corresponding to each weight function, and this will give us as many equations as are constants assumed here. So right now we have only one constant. We get only one equation, but turns out that this constant is getting cancelled here. So that means for any, there will be infinite number of solutions for this, for C1. We can have any C1 and still get the solution. So we would need to solve this integral. These are very complicated integrals. I won't go into much depth in this, and we can get. I think we can solve for lambda here, since it is an unknown. Fine. We'll take solve further more problems for variables later. So next, move on to the following problem. So this is, I think, pretty straightforward, simple problem. I want you guys to answer this. For a given problem defined like this is the boundary conditions: u at 0 equals to 5 and du by dx at x equals to 5 is 1. Determine the type of boundary conditions. So first of all, these are the boundary conditions here. So what type these boundary conditions are? What are these boundary conditions called? Basic terminology.
Is it Dirichlet and Newman boundary condition?
Yes, right. So when we specify the value of the primary variable, that is in this case that's u, so that's called Dirichlet boundary condition. And if we specify the derivative of that primary variable, or this is known as secondary variable, this is known as the Neumann boundary condition. And both of these are non-homogeneous boundary condition. We don't have zero. Fine. So find the bilinear and linear term in the following differential equation. So yeah, how do we do this problem? How do we start this?
For the bilinear part, we have to choose variation for xi.
Right. Actually, for both, we have to follow simple procedure for getting both, and that is we have to write the variation statement. So, how do we start writing the first of all, yeah, this is just to make clear that xi is the primary variable. Lot of variable in this equation. So, how do we write the variation statement?
We have to assume that say V is the variational statement for xi.
V is the variation for xi. Assume a variation V for xi, and with the help of this variation V, we write the variation statement, and that is done by multiplying the equation with the variation and integrating it over the domain just like okay, the constant is k. All right, so next is we do integration by parts. And the simple trick for that, we write the integration term with a negative sign, and we transfer the one derivative on from the primary variable onto the variation. We left with dxi by dx, and then we write the boundary term. So boundary term is the variation times one derivative less on the primary variable with on the limit x1 to x2. Then we have our term okay. So I have not given boundary condition here. Never mind. We'll just write the boundary term as it is. In that case. Okay, so which is the bilinear term and which is the linear term here? Anyone? Anyone who has not answered before would like to try?
LHS is bilinear.
Yes. So it is an operator on the variation and the primary variable, and it is linear in both and symmetric also. And right hand side is the linear, of course. So it is only an operator on variation B. There's no, it's okay. Okay, yeah, I missed this. So turns out that RHS is also bilinear term. See, we have psi also here. Okay, that's interesting. Yeah, I missed this. So this is also a bilinear term. It turns out the only boundary term that is remaining here, this is function of b only. It is not a function of psi. And don't let this d psi by dx confuse you, because that is a constant value defined on x1 and x2. Okay. So turns out apart from boundary term, both the integral terms are bilinear term. I think I'm not sure about calling this as linear term because there's no operator on it, particularly in some integration statement. I'm not sure if this is even called an operator. But rest the two integration terms are both bilinear terms. Okay. This LV, I believe it is a linear term because usually we don't, if we have it boundary integral term, we usually write it as v times d psi by dx times some n d gamma, and this is some constant. We are ultimately left with v into some constant times this integral over the boundary. So I believe this is a linear operator on v. But don't worry, this is not of much use later. If there's any doubt, you can still ask. Okay, so can we move on to the next problem? Okay, this is an interesting problem. So this is an actual minimization problem that I found out. So the solution to it is pretty straightforward. You don't need to write mathematical equation to guess the answer. Can anyone still guess the answer? We have 2 points. Point A, x1, x2, sorry, x1, y1. And we have another point B, x2, y2. So the question is, what curve between these 2 points will have the minimum length? So first of all, without even solving, what is the answer for this?
Straight line.
Exactly, straight line. Curve of the form y equals to mx plus c. This is the answer for this. We know this. But how do we pose this as a minimization problem? Anyone? Any guesses? First of all, what are we going to minimize? What? physical quantity.
Distance.
Yes, the distance between
Y
the
with
point.
respect.
Yeah, so it is the distance between the point A and B that we are going to minimize. And how do we represent the distance into an integral statement? That is the question. So we can take a very infinitesimally small part of this the curve between the two. We take this curve ds. So basically we need to, if we integrate this curve ds between point A and B, we get our total distance between A and B, isn't it? And how do we get this ds?
Root of x square plus dy square.
Exactly. X square dy square. Okay. And if we take out dx from this root term, we'll be left with 1 plus dy by dx whole square times dx. Now this is an integration in terms of x. We can write x1 to x2, 1 plus, we can write y dy by dx is y prime. So this looks like a function to you, isn't it? So find y such that t is minimized. Okay, so that's how we can pose, pose a minimization problem for this particular question. Is it clear?
Yes.
So can we try to solve this? We have time. So how do we solve this? First of all, the Euler-Lagrange equation is df by dy minus d by dx of dou f by dou y prime. This term is 0. We don't have any y. And the derivative of this function with respect to y prime is, okay, it's 1 plus y square. And 1 plus 2y dash equals 0. So I think we'll get differential equation of this form. Okay, we have to, okay, this whole the derivative over it, d by dx. So if we integrate with respect to dx, we'll have minus 1 plus y prime square equals to constant, or you can just drop this minus, that doesn't matter. So the differential equation is So we get dy by dx equals to some constant c square upon 1 minus c square, right? This is m. And if we integrate this, I don't have space here, I'll do it above. So dy by dx equals to m. We can write dy as m dx and integrate it both sides. We'll get y2 minus y1 between the limits equals to m times x2 minus x1. So this is the equation of, okay, no, sorry, that's not how we do it. We'll get y equals to mx plus c, and then we'll apply these boundary points to get c. So see, we get the equation of line as we expected the answer to be. So the way we solved got the minimization problem, and then we solved the Euler-Lagrange equation, got the differential equation for this problem, and then we solve it to get the solution y. Is it clear, right?
Yes.
Okay. If there is no further doubt, we can move forward. Okay, find the weak form for an axial deformation in a bar having these values. Uh, distributed load. Use the principle of minimum potential energy. That is basically minimization of the functional for the energy, potential energy of the system. So uh, how do we get to the variational statement? So it's vice versa. So from variational statement, we can go to the minimization problem, and from minimization problem, we can write the variational statement. So what should be the expression for the potential energy of this axial deformation problem? Pi is equals to anyone? Just what will be the constituents of the energy, potential energy? So we have a bar. Yes, sir. Please. To say something?
I was about to say strain energy.
Yeah, exactly. We have one component as strain energy. That is right. Apart from that, what other another thing would constitute to the potential energy?
Work done.
Work. Yeah, exactly. That's the work done. So here, for a one, so we're considering a 1D bar for simplicity. So what is the expression for that? Half of EA du by dx square. Correct?
Yes.
And then this is integrate over the entire length to 12. And then for work done, we take negative sign. we have the distributed load times, I think, the displacement. Yeah, force into work is basically force into displacement, isn't it? This thing integrated over the length. So this should be the expression for the the potential energy. So in order to minimize the potential energy, uh, there's the one new thing I would like to introduce. I think we have not covered in the video lecture so far. So we can directly take the variation of this function. Right. So whatever expression, so basically minimization means first variation is equal to 0. So how do we find the variation of pi? Use this variation operator, and this is an interesting operator and very fun and helpful. Du by dx dx. So this variation operators work same as the del operator. So it can just go inside and take the derivatives. So we have half ER constant. We have du by dx, that is a function of u. Our primary variable is u, so it should act on it. So we have 2 times du by dx, and then it will act on del of du by dx minus, then go to the next term. This simply goes on u, del u dx. So there's property that this d can go inside. So if we are writing somewhere as d of du by dx, this is same as writing d by dx of del u. These two things are same. So we can move this inward here. So 2 get cancelled. EA du by dx times du by dx of variation of u times dx minus rho and variation of u dx. Okay, so del u is the variation. We can just simply substitute this with v. So what we get here is 12 EA du by dx to dv by dx equals to rho v dx. So now does this equation rings any bell? Does this look familiar? Anyone?
AUV is equal to LV.
Okay. You mean this term here, right? AUV. Yeah, this, okay. You mean to say AUV equals to L, exactly. So this is same as AUV equals to L, which is our variational statement or weak form. That is what we wanted to get, right? So one thing we can see here is that if we want to go from variational statement to the minimization problem, we need to first check the bilinearity and symmetry and linearity of L, and then we can just get our variational statement as half of AU comma U minus LU. And if we want to go opposite from a minimization problem to the variation statement, we can just take this variation of our functional and equate it to 0, and we can straight away get to our weak form or the variation statement. Fine. Is it clear? Is there any doubt I'm going too fast or too slow? You can stop me anytime. Okay, so if there's no doubt here, we can move forward. So this is a simple problem. We need to verify if the given operator I is symmetric and bilinear. So can we check if it's bilinear? But first of all, it's an operator on U and B. So first we need to check linearity for U. So is it linear in U? And even you guys can just simply answer this question. Won't go into much depth here.
No.
Yeah, so it's not linear in U. So we have uh, two terms for U, this one and this one. So if we try to break it as IU1 plus U2, we won't get IU1 plus IU1 plus IU2. So it's not linear in U. But is it linear in V?
Yes.
Yeah, it's linear in V. We only have one term for V. So no, it's not bilinear. That's obvious. It's just linear in V, not linear in U. Not bilinear. And is it symmetric?
Yes.
So you need to say V instead of IUV, if we write IVU.
Oh, no.
Yeah. So we get V dV by dx dV by dx. This is not same as the above. So it's not symmetric. It's not a symmetric and bilinear operator. I hope you get an idea of what bilinear and symmetry means. Okay, so then we have one more question. We have to solve this problem using Rayleigh-Ritz method. Okay, so I would need help from you guys. First of all, how do we start solving using a Rayleigh-Ritz method? Solving a problem using Rayleigh-Ritz method. Anyone? What are basic steps in solving problem using Rayleigh-Ritz method? Anyone? Any idea? Okay, so I'll just move forward. So first thing is we can do either. So for one thing we can do is we write the variational statement. So I'll just quickly write it. I haven't mentioned the domain. So we have minus of du by dx times du by dx. Then we have v times du by dx 0 to 1. Okay, so this should be this. Because we can't specify Neumann and Dirichlet at same point, so it has to be different. And then we have this stuff. So this would be our variational statement. I'll further simplify this as then we have at x equals to 0, we know du by dx. So we have v at 0 times du by dx is 1. So we'll be left with this v, the value of v at 0, minus we have at x equals to 1, u1 is defined. So the variation there, that is v1, should be 0, because when the value of where the value of the primary variable is known, its variation becomes 0. We'll be left with v0. Okay, so we got our variation statement here. Now next thing is assuming solution. So we can assume u1 as c1 by 1 plus phi naught. So to keep it simple, we will just use one approximation function, c1 phi 1 and then phi naught. So phi naught should satisfy the Dirichlet boundary condition, right? And the Dirichlet boundary condition here is at u equals to 1, phi naught equals to 1. So one simplest approximation can be phi naught equals to 1, or phi naught equals to x, then also it satisfies the boundary condition, right? We'll go with phi naught equals to x, and phi 1 should satisfy the homogeneous form of the Dirichlet boundary condition. What can be the approximation for phi 1? We can't put it to 0. There won't be anything left to solve. We can use should give 0 at x equals to 1, or you can write x minus 1. Is it fine? For x equals to 1, we get 0. Okay, fine. So now substitute the value of u in the equation. First of all, and v equals to 5. So du by dx is c1 plus 1 and dv by dx is 1. Okay, so now we substitute this in the variation statement. We have 0 to 1, dv by dx is 1 times du by dx is 1 into 1 plus c1 times dx equals to, and v is v is v1. v1 is x minus 1, x into x minus 1 dx plus v, value of v at 0 should be minus 1. So we have 1 plus c1 x element 0 to 1 minus we have x square minus x, that gives us 2 by 3 minus x square by 2 element 0 to 1, then we have minus 1. So we have 1 plus c1 equals to 1 by 3 minus 1 by 2 minus of 1 by 3 minus 1 by 2 is basically 1 by 6, right? Minus 1 by 6. So c1 equals to 1 by 6 minus 1 minus 1. So it's 1 by 6 minus 2 will give us 12 minus 11 by 12.
Minus 11 by 6.
6 or 12? Oh, 6, yeah, yeah,
6,
okay,
sir.
6. Okay, so
Okay.
this would be the value of c1, and so our solution becomes u of x equals to minus 11 by 6 x minus 1 plus x. So I hope I didn't make any mistake here. So hopefully this was clear for everyone. If there is any doubt, you can please ask now. And if there's any doubt anywhere so far, we are free to discuss it now. Okay, is there any doubt? Otherwise, I think we're out of time now. So if there's any doubt, you can please ask, or we can conclude.
Hello?
Yes, sir.
Hello, sir. So the fourth one.
Fourth problem.
Yep.
This one.
Once explain this.
So it's just simple, straightforward question. We are given a problem with this differential equation d square u by dx square minus fx equals to 0, and we're given two boundary condition: u at 0 equals to 5 and du by dx at x equals to 5 equals to 1. So the question asks, what are the name of these boundary conditions? Sorry. The question is, we have given two boundary conditions, this one and this one. So it just asks what are the two name of the two boundary conditions. So what I mentioned before is that whenever the value of the variable itself is specified anywhere, that is known as the Dirichlet boundary condition or the essential boundary condition. And whenever the derivative of the primary variable is specified, or it is also known as secondary variable. Then that is known as the Neumann boundary condition or the natural boundary condition. Okay.
Okay, sir.
All right. Is there any other doubt?
No, sir.
Okay. So if no one else has any doubt, we can. I think we can conclude the session, and you guys can log out now.
Thank you
We'll
so
see
much,
you in
sir.
the next session. Yeah. Thank you so much, sir. And if there are any feedbacks, I would love to have.
Thank you, sir. Thanks for coming.
Thank you.